thanks to the organizers for allowing me to present this poster today. I'm Saurabh. I'm a PhD candidate at the University of Calgary working with Professor Christoph Simon. Today I'm going to tell you guys about one of the projects in our group aimed towards developing long-distance quantum networks with superconducting processors. The grand long-term motivation for a quantum network is towards designing a quantum internet, which is going to be analogous to the classical internet of today, but much more secure and powerful in certain aspects. Now, the internet can be broken down roughly into two components. One is the computational unit, and the other is the communication unit. For a quantum network, and hence the quantum internet, there need to be quantum processing nodes which are linked together via quantum channels. Superconducting processors are one of the leading candidates for building the first generation of quantum computers. We propose to use cat states in microwave cavities as our qubits and manipulate these cavity states using the strong superconducting qubit-cavity interaction possible. This architecture has several advantages, as enumerated here, particularly in terms of the coherence times, which is important for long-distance networks. However, these cavity states are in the microwave domain, which is too low in energy to carry quantum information over long distances at room temperature. To convert them to telecom frequencies suitable for such communication, we propose to use a specific rare earth ion doped crystal-based transduction protocol, as shown in this schematic. However, other promising transducer approaches, for example, electro-optomechanical approaches, can also be integrated in our architecture. Now that I've discussed the local architecture in some detail, let me get to the part of linking distant quantum computational nodes. An important requirement to link the nodes quantumly is to be able to share entanglement between those. Let's just take two nodes, node A and node B. Node A could be in Ottawa and node B could be in Montreal. We develop a robust entanglement distribution protocol based on heralding, after the photons coming from these nodes interfere in a beam splitter placed in between these two nodes. For longer distances, we develop a quantum repeater protocol based on the same architecture. An important metric for a quantum repeater is the entanglement distribution rate. This is a comparison of the entanglement distribution rate versus distance for a number of repeater schemes. We show that ours could be higher than other promising approaches, even when considering realistic losses and imperfections. So to summarize, I talked about a robust way to distribute entanglement between distant quantum computing nodes based on orthogonal cat states of the microwave cavities as qubits and rare earth ion doped crystals as transducers. We then designed a quantum repeater architecture with this framework. As an outlook in the quantum computational aspect, it is of interest to think about how best to connect different units to efficiently distribute an arbitrary computational task. And regarding the quantum communication aspect, one will need to figure out efficient repeater architectures for a truly global network, possibly using both ground-based and satellite links. With this, I thank you for your time. Hope you have an excellent rest of the workshop.